Hey everyone, welcome. Today, we're going to tackle a coding pattern that is, and I'm not kidding, an absolute game changer for your coding interviews. It's called the two-pointers technique. You know those solutions that get super slow as you add more data? That's what we call O of n squared. Well, this technique takes that and turns it into a lightning-fast O of n solution. It's a huge deal. So let's just dive right in and see how it all works.
Okay, and this right here, this hits home. I mean, we've all been there, right? You're staring at a problem, you finally get a solution that works, but deep down, you just know it's clunky and slow. It's that awful feeling of regret, thinking, man, there has to be a smarter way. Well, today, we're getting rid of that feeling for good. This isn't about memorizing a trick, it's about building a real, solid intuition for solving problems the right way.
So where does that slow, clunky feeling usually come from? Well, it comes from what I like to call the brute force trap. It's that first idea that pops into your head, the one that feels so obvious, but man, it is often the slowest road you can take.
And this visual just says it all, doesn't it? On the left, you've got the slow way, the nested loops. For every single thing in your list, you loop through every other thing. It's like checking every possible combination. Yeah, it works, but it's a mess and it's slow. But look at the right. That's the smart way. You've got a left pointer, a right pointer, and they just move intelligently. It's so much cleaner, so much more elegant, and believe me, it is way, way faster.
And that brings us to the hero of today's story. It's time to leave that brute force path in the dust and talk about a much, much smarter way to get things done. So, what exactly is the two-pointers technique? Well, at its core, it's just about using two little markers or indices to scan through your data in a really smart way. Instead of that messy nested loop approach where you compare everything to everything, you just make one single clean pass. The whole game is moving those pointers based on some simple logic. The key words here are scan data smartly.
And here is the payoff. This is why we care so much. The result? Your time complexity just plummets from O of n squared all the way down to O of n. And let me tell you, for a big chunk of data, that is a massive difference. We're talking about going from "this might never finish" to "done in a split second." In an interview or a coding competition, this isn't just a nice little optimization, it's literally survival.
All right, that's enough theory. Let's get our hands dirty and actually see this thing in action. We're going to start with one of the most classic problems you'll ever see, finding a pair of numbers that adds up to a specific target. Okay, so here's the setup. We're given a sorted array, and I'm going to say that again, sorted, because that is the secret sauce here. Our array is 1, 2, 4, 7, 11, 15, and our target sum is 15. The question is simple. Is there any pair of numbers in this array that adds up to 15? Now, the brute force way would be to check 1 plus 2, 1 plus 4, 1 plus 7. You get the idea. But we know a better way now. And boom, here is the solution. Just look at that. It's so clean, so simple. All we do is set up a left pointer at the very start of the array, index 0, and a right pointer at the very end. Then, we just have one while loop that runs as long as left hasn't crossed right. So let's actually trace this step by step to see the magic happen. Okay, first up, our left pointer is on the number 1 and our right pointer is way over on 15. What's the sum? 1 plus 15 is 16. Well, our target is 15, so 16 is too big. Now think about it, since the array is sorted, how can we make the sum smaller? We have to get rid of the biggest number, right? So we move our right pointer one step in.
All right, round 2. Left is still on 1, but now right has moved to 11. Let's add them up. 1 plus 11 is 12. Okay, this time our sum is too small. We need to get a bigger number. And again, since the array is sorted, the only logical way to do that is to get rid of our smallest number. So we move the left pointer one step out.
Okay, here we go. Left has now moved to the number 4 and right is still on 11. Let's check the sum. 4 plus 11 is 15. Bingo, we've found it. It's a perfect match. The code immediately returns true and we're done. Look at that. We didn't have to check all those other pairs. We just zeroed in on the answer.
But hold on a second. This feels almost too easy, right? Why does this actually work? I mean, how are we so sure we didn't accidentally skip over the right answer? And this right here is the whole secret. It works because the array is sorted. That one little detail is everything. Because it's sorted, when we move our pointers, the sum changes in a totally predictable way.
If our sum is too high, moving the right pointer in is guaranteed to make it smaller. If the sum is too low, moving the left pointer out is guaranteed to make it bigger. We're never guessing. We're systematically eliminating all the wrong answers.
Okay, awesome. Let's check out a different kind of problem to see how flexible this pattern really is. This time, we're not just looking for something. We're actually going to change the array itself, and we have to do it in place.
So here's the deal. We get a sorted array that has a bunch of duplicates, like 1, 1, 2, 2, 3, 3, 3, 4. Our job is to squish it down so all the unique numbers are at the front. And that in-place part is crucial. It means we can't just make a new, clean array. We have to do it right there in the original one.
So how do we pull this off? Well, with another version of two pointers. This one is often called the slow and fast pointer approach, or sometimes the tortoise and the hare. We have pointer I, which is our slow pointer. It's going to mark the spot for the next unique number we find. And then we have pointer J, our fast pointer, which just zooms ahead through the array looking for new, unique values.
The logic is actually pretty simple when you think about it. Pointer J, the fast one, just scans through the whole array. Pointer I, the slow one, just chills. The moment J finds a number that's different from the one I is pointing to, we know we've found a new, unique number. So we nudge I forward one spot, and then we copy the value from J over to where I is now. We're basically just overwriting the duplicates as we go.
Okay, you ready to level up? Let's tackle a real challenge problem now. This is a super common interview question, and what's tricky about it is that on the surface, it doesn't scream two pointers. Okay, here's the problem. Imagine you have an array of numbers, and each number represents the height of a vertical wall. Your job is to find two of these walls that, if you put a floor between them, would hold the absolute most water. And the amount of water you can hold is, of course, the distance between the walls, the width, times the height of the shorter of the two walls. And here is the elegant two-pointer solution. We start with our left and right pointers at the very ends of the array. Why? Because that gives us the widest possible container to start with. Then, in our loop, we calculate the area for our current container and check if it's the biggest one we've seen so far. But then comes the big question, the key to the whole thing. Which pointer do we move? Do we move left in or right in?
And this is the brilliant logic behind it. The area is always limited by the shorter line. Think about it. If you have a short wall and a tall wall, and you move the tall wall's pointer inward, what happens? Your width gets smaller, and your height is still limited by that same short wall. So your area can only go down. There's no way to get more water. Your only hope, your only chance of finding a bigger area is to get rid of the short wall and move its pointer inward, hoping to find a taller wall.
Okay, so we've seen this pattern in a few different forms, but the most important thing is knowing when to actually use it. How can you spot a problem in the wild where this is the right tool for the job? Let's build a little mental checklist.
So here's your rulebook. First big signal, you see a sorted array or a sorted string. That should immediately make you think about two pointers. Next, if the problem is asking about pairs or triplets or subarrays with some specific property, yep, good candidate. If you literally see the phrase, find two elements such that, that's a dead giveaway. And like we saw with the duplicate problem, if you need to remove things in place or compare things from both ends of a list, this pattern is almost always your best bet.
And let's end on this one thought, because I think it sums up everything perfectly. Brute force just plows ahead and checks everything. It checks every single combination, even the ones that are obviously wrong. But two pointers, it's smart, it's efficient. It uses logic to completely ignore huge chunks of the problem that don't matter, and it focuses only on the possibilities that could actually lead to an answer. It really is more than just a technique. It's a much smarter way to think about solving problems.